little bit. So is this better? Or the white was better?
This looks good.
Okay. Yeah, actually this color doesn't hit the eyes that much. Um, okay, so what we were discussing last time is about integrable functions, right? So is this part clear? So things are quite bit, or I mean, well written in the notes. So you can read from the notes, but the main idea, try to understand the main idea for a discontinuous function when it is integrable. So what is the idea? The idea is on the point of discontinuity, you try to make the subinterval which creates the partition very small, as small as you please, and the rest of this you have the partition, usual partition. That is the main idea. So near the point of discontinuity, you make the length of the partition small as you please, and other part your functional value is small when there is partition becomes smaller. So that is this is the main idea. Now this idea is implemented for the following things also.
Sir,
Yes,
sir, I had a question from generally from integration. May I ask it now?
integration.
I have a question from integration. Like the theory that we now are doing,
Yeah,
it basically relies very much on the order of the real numbers, right?
that is true. Order of the no, actually the partition. So order doesn't matter as such. You see here, of course, we have taken this kind of stuff, but this is actually the length, right? This is the length, and
Hmm.
you have taken what is supremum, right? Yeah,
Hmm.
this somehow, of course, we have used ordering of real line because of this partition, and you xj minus 1, that part we use the partition. Yeah. So ask your question.
Yeah. So if we have a function, the domain of which is not a set which can be ordered, like suppose the domain is
Mhm.
R2, then how do we define integration?
Yeah, so then you need to define R2 is simple, right?
Yeah, for
R2
R2 maybe it's simple. I was thinking of it, but for something more complex than R2, how do we define integration?
for more complex R2, then you have to define. So the point is, see, if you understand how to define R2, you will be able to understand how do you define the other sets. So for example, if you have R2, so what you will do, you will look at small rectangle, right? Small rectangles. Somehow you look at small rectangles, or you first, there's two things. First thing is your variable was x and y, and if your domain is rectangle, so if your domain is rectangle, right, and if your function from this, let's say r, so this is not the sort of real number, this is the rectangle r, 2, and you want to define this one dx dy, right? So here what you want to do, you want to define this to be first, let's say this is AB. So I would like to
Sir, could you change the background color back to white?
What? I didn't get what? Sorry.
So could you change the background color back to white?
Background?
Back to white, like the background thing you're writing on.
Oh, okay. So yeah, you back to white. So that is better.
Yeah, yes. Yeah.
All right. So let me. Yeah, I need to change the font color as well. So maybe I should put this. Yeah, is this fine?
Yeah, sir.
Right? Is this fine now?
Yeah, it's yeah.
So we are actually. So the question is, what happens if you want to integrate or not? Right. So the problem is this is f of xy dx dy. So the point is, uh, let us look at, so since I have taken 0, this is x-axis, y-axis, so it would be 0 to this one. This is 0. Let's say 0 to A, and this is 0 to B. So here first 0 to B, and then 0 to A, f of x, y, dx, dx, then dy. You will define this way. All right.
So basically,
Now,
we basically okay.
yeah, you use just in R2, in R, right? So this is the integration with respect to x. Y is a fixed variable now, and then you this is repeated integration. You will define this to be same as this, or I mean it doesn't matter if you change the order, dy and then dx, right? So you will consider those functions which does this order doesn't matter, and you will define this way. And then if you have complicated domain, what you want to do is you want to divide into some rectangle. And smaller and smaller rectangle you take, and like this will be function is defined on this one, and then for each for each rectangle you know how to integrate, and you do that and sum it up, and let the area of the rectangle goes to 0. This small area, so it becomes smaller, so you divide more and more to approximate this region. So that's how one defines integration in in multivariable. And of course this is so mostly what you will see in calculus is taking rectangles, cubes, etc. And later on you will see that you can integrate over the sphere also. So those things can also be done, but then this notion of these things should be properly defined there in complicated spaces, uh, and that can be done. And then what? So this Riemann integration, same as what Lebesgue has done, that is Lebesgue integration for the function which are continuous and stuff like that. So Lebesgue's integration is is of course for general spaces it is more easily defined. Once you have a concept of measure, and it's much more general, therefore one could go to Lebesgue integration and define integration over there for more general region. So what Riemann's integration is kind of Rn one can do in this way, but even this complicated surfaces, complicated stuff, one one need somehow to approximate by rectangles or cubes to get the integration, right?
Sir, so basically, when we are approximating with cubes or maybe four-dimensional cubes, we are basically talking about Rn.
Right,
So when we defined it on Rn, we are basically using our notion of integration on R and extending it, repeating it to make it to Rn.
right.
But if we have a space where, that's what I was about to ask actually, if you have a space where this notion of a rectangle or a cube is not defined, we don't have a
Yeah.
notion. Like last year, we studied that matrix. There can be many forms of matrix spaces.
Oh,
So,
so metric space you can neither you can neither you can differentiate nor you can integrate on metric space just in a metric space. So you need more structure on that.
oh, so on
You
matrix
need
spaces,
more
it may
structure.
not be defined. Okay.
Yeah, for general metric spaces, integration differentiation may not be defined. So, for example, suppose you have football and you have function from this football to a real number and you want to integrate on there, right? So there you can actually do things like this. So you look at a small region, small portion. So generally, those things are kind of pentagon or hexagon or whatever, right? So this looks like one can give a map that would look like rectangle here, or you can just look at rectangle out of here. So now on this, so this map will be homeomorphism properties like that. So homeomorphism is important. Now integration on this region, you would now function restricted to here is there, and you go via this one. So if this is phi, then you have a composed phi inverse. Now you would say integration on this one, this region, if is defined to be integration of a composed phi inverse. Like that. So one can define this way, and then like here, you cover it up, and for each of such thing, you get such integration and sum it up to get the whole integration on the whole. Well, that is the idea behind integration for general surfaces. You will see this. Those who will be taking mathematics can see this in curves and surfaces course, how to integrate on a surface. So this is a standard example. So sphere is a standard example of surface where one can do integration. All right.
Yes,
Yeah.
please.
But general metric spaces, those things are not defined. You have just a concept of distance. So concept of topology is there. So at most you can go with continuous function. That's it. And distance preserving maps and all this stuff are there.
So, what are the other notions that we need to integrate on a surface?
So the point is on a surface should be inside R3 or should be some maps like that. Right, surface are in R3 in Rn, right? So you look at things are inside R. So you have those kind of maps. Okay, so that is important. Those kind of maps, which is homeomorphism to R2 here in yeah, for surfaces it is R2. and then you
No,
can define.
by surface I mean any structure. I used a wrong word. I mean in any structure, what are the other things that we need apart from distance to define integration?
Yeah, apart from distance, what do you need? You need to have some uh, so you need to somehow come to Rn corresponds to some Rn. Okay, that part is needed. Or what concept is general concept? So that is true for Riemann integration. So if you want to define Riemann integration, you should somehow associate with some Rn locally at least. But in general, for a metric space, so you don't need actually metric to define integration. Okay. So for metric space, what you need a measure to define integration. So measure with some space with measure is called actually measure space. So one need a topology. So concept of open set should be there, and concept of a measure on open sets, closed sets, compact sets. Those things should be there, and then you can define the integration on the function on the space. Okay.
Yes, sir. Yes, sir. Got
Yeah. So this is the concept you need, which is measure. In this case, in our case, measure is the length. So yeah. So this actually gives a measure, which is length in our case. All right. Any other question? Yeah, this is an interesting question. Uh, of course, you should think things like that. Yeah, the distance doesn't play that much role in defining integration. What measure does, and you need to have some property in the topology. So open sets should be there. All right. So let me write the things which we have done already. Uh, so class of all integrable function, Riemann integrable function. So firstly, this it contains all continuous functions, contains functions with finitely many discontinuities, contains bounded function. All right. Third thing, what is contains bounded functions whose points of discontinuities form points of discontinuities has finitely many limit points. So 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 is the last third part clear? The proof is same as the previous. The second one. So is the third part clear? So what we have is we have few limit points. Okay. So assume we have three limit points: a naught, a1, a2, right? And you have these are the point of discontinuities have these limit points, and there are several points of discontinuities, right? Now, what does limit point means? Yeah. So take any neighborhood, it will contain all but finitely many points, right? So there will be only finitely many discontinuities out there, out of this neighborhood. In this case, we look at this neighborhood and we look at this neighborhood. Okay, as small as we please. So this one is the corresponding thing like this. Okay, as we do it here for the point of discontinuities, we will do now for the limit points. So these are limit points. There we take small neighborhoods. Now in that neighborhood, almost all the continuities, the point of discontinuities will be there, right? Except finitely many, right? So in this three neighborhoods, outside this three neighborhood, you have only finitely many discontinuities, right? Yeah. So there, this is integrable. This part also, on this part, the condition on the partition lower sum minus upper sum is less than epsilon is satisfied. On this part also it satisfies, right? Lower sum minus upper sum. Now on this part, what do we do? We would mention we would make this neighborhood as small as we please, so that capital M minus small m here on this neighborhood and on this neighborhood, that may become little bit larger. Of course, this cannot go to infinity. Uh, we have the function bounded. So, but the length of the interval so small that the sum m minus capital M minus small m times the length of the interval will be less than smaller. Is it clear? So here you might have several discontinuities. But here the discontinuities will have some limit points. You might have here several discontinuities. Discontinuities will have limit points. Like this, whatever. But this part, here will make so small, the length is make the length so small that capital M minus small m times the length so small in the sense this one, so delta, this is a naught minus delta by 2 to a naught plus delta by 2, a naught minus delta by 2 plus delta by 2 minus a naught minus plus delta by 2 So this would be delta times m minus, which is very small, which is very small. Well, in the notes, the most general theorem is given. Uh, I have taken this Riemann's paper and actually line by line what need to change and what is the current language. Those things are written, and the most general theorem has been proved in the notes. So please read that one. That I'm not going to present in the class because that is quite a bit of technical. But what you need to know is this class of functions. This class of functions are there in the class of all Riemann integrable functions. All right? Yeah. And the proof for this one is the idea is almost same. So try to use the similar idea here to prove this third part. It will be kind of an experience for you to how to write the proofs, having one proofs. So this proof is not there in the notes. So this proof you do it. This contains one singularity, so one discontinuities is there in the notes. It is all written, so that gives you for finitely many singularities, finitely many discontinuities also, and this one it will have finitely many limit points, but you need to apply the same proof, um, the technique of the same proof here, making the limit points that way, taking the neighborhood, the small limit points smaller. All right. Any question here? So read the notes for the most general theorem about Riemann integrable function. Well, I'll upload this one, all the notes today itself. But let me give one other kind of function composition. When a composition to function Riemann integrable. So before that, let me state following fact, and which is easy to prove. Uh, Collection of all Riemann integrable functions forms a vector space. Right? Is this clear? Is this clear? What do you need to show?
Just the basic axioms, so closure over addition and multiplication with uh, real
Right,
values, another number.
right, right. So you need to show. So this is exercise. Show that. So if f and g are Riemann integrable, then f plus g are Riemann integrable on AB, then f plus g is also Riemann integrable on AB. So this is very simple. You take a partition for A, and you look at partition for G as well, and then you take common refinement, and there you look at lower sum minus upper sum. Okay, for F plus G, so lower sums correspond of F corresponds to lower sum F part, and similarly for G. All right, few more properties, and then yeah, this is one and two. If F is Riemann integrable, so that constant times F is also Riemann integrable for C belongs to R. So on the same interval AB. All right. And then a few other facts. Suppose if G are two functions from AB to R such that fx is less or equal to gx for all x in AB, then integration a to b fx dx is less or equal to integration a to b gx dx. Right? So how do you prove this? Yeah. So this one is Riemann integrable. You need Riemann integrability to define integration, and it satisfies this inequality fx is less or equal to gx. So how do you prove this integration is less or equal to integration af less or equal to integration g?
Look at G minus F.
Yeah,
Then you can show that that will always be positive because all of the Riemann sums are positive.
right. So yeah, so int look at g minus f so that whatever the upper sums or lower sums, actually the Riemann sum, you go with Riemann sum. The Riemann sum. So what is the Riemann sum? Riemann sum is this one. I didn't mention, but this one is called Riemann sum. So this one is called the Riemann sum. So that the Riemann sum is non-negative. All right. And then you can have this one, integration a to b fx dx is equal to integration a to c. C is the point between a and b fx dx plus integration c to b fx dx. So this you know from the school. Now you can prove it. Just looking at the either, yeah. So partition, divide this partition into, make a refinement so that C is a point of the partition, and then separate these two partitions. One is from A to C, another is from C to B, and then you get this two. All right, any question here? Three, suppose F is Riemann integrable on AB, then F is bounded. So boundedness is not required actually in the definition. What is required is that your infimum and supremum is bounded on small part to define Riemann sum, as to define the upper sum and lower sum. Now the point is, since you look at you look at a partition, each of the partition will have this property. Your capital Mi and small mi must be finite number, and now you have finitely many partitions, so that gives you have to be bounded. Right? If upper sum is equal to lower sum, and of course these are not infinite, then you will get have to be bounded. All right. Fourth is suppose f is Riemann integrable and mod of fx is less or equal to m for all x in AB, then integration f a to b fx dx is less or equal to m times p minus a. This is very simple, right? There's nothing to prove actually. You all you do this. Each of the subinterval you make this bounded by n. So you compare with f and the constant function n, and that will do the job. And of course, yeah. So, and the first one would give you that. All right. Now, so a few more exercise. So this will be part of the next assignment. So if f and g are Riemann integrable, well, then fg is also Riemann integrable. All right. So yeah, so you need to use some things here. but what I mean, you need to use some things that we are going to prove next. The composition of functions. So this is a theorem. Suppose this is not in the notes, so I'll send it. I'll upload this one. So suppose f is Riemann integrable on the closed interval AB and small m less or equal to fx less or equal to capital M. The image lies in an interval small m to capital M for all x in AB. And yeah, suppose further that phi from small m to capital M to R is a continuous function. And define hx to be pi compose fx, right? F takes x to small m to capital M in interval small m to capital M, and then phi takes fx to R, right? On AB. Then H is Riemann integral. So we'll prove this on AB, but before that one, let me give an interesting application. So an application is an application. So if f is Riemann integrable, then f square is Riemann integrable. And you now go on x cube, x to the power 4, x to the f to the power 5, all this, right? So, and this one also comes as a corollary to this. So this is interesting. So let's prove this. Let's give a proof of this. So proof. So fix an epsilon greater than 0. So phi is continuous on a closed interval. So phi is continuous on closed interval since not AB, small m to capital M. Phi is uniformly continuous, right? So which means for this epsilon, that means there exists delta greater than 0 such that mod of s minus t less than delta implies phi s minus phi t less than epsilon. All right. So this is the one. It comes from uniform continuity. And where does st belong? St belong to this interval mm. All right. So this is from uniform continuity of phi. Now we look at the Riemann integrability of it. Since f is Riemann integrable on AB, so epsilon is already chosen. So there exists a partition P, which is x0, x1, xn of AB, such that UPF minus LPF is less than epsilon. Oh, well, we need to consider C. We need to look at the composition. So instead of epsilon, we would consider so corresponding to delta. So corresponding to delta square actually. So called delta square. So this is a small trick which will be used. Corresponding to delta square, you have a partition such that this becomes less than delta square. So Mi is as defined the supremum of f over x mj xj minus 1 comma xj and small mj infimum of f xj minus 1 xj. All right. So mj, so j equal to 1 to n, this as it is. Now we need to find the supremum for h, right? So define mj star to be supremum of h on xj minus 1 to xj and mj star to be infimum of h over xj minus 1 to xj, right? So corresponding to this partition, you do it for h, and we'll show this partition actually would work in some way. Let us see how. Now you consider the set A. Consider the following set. The set A. J belongs to 1 to up to n, such that what? Mj minus small mj is less than delta. You collect all such integer j which lies in 1 to n such that this on a interval xj minus 1 to xj, this the difference between the supremum and infimum is less than delta. You collect all of such j's and call it A. And B, and consider the sets A and B to be j in 1 to n, which is just complement of A in 1 to n, which means this m j minus small mj is greater or equal to delta. All right. So B is a complement of A in 1 to n. Now suppose for each j belongs to A, get from this one, from where? From here, right? One that mj star minus small mj star is less than epsilon, right? So we just use this one. We use this one. So here, the only thing we need to make sure is partition of AB such that two things, xj minus 1 is less than delta. This is true for all j. We need this one also because we will use this, and we need this too. All right. So if j belongs to A, it works. The supremum of h minus infimum of h on that small interval is less than epsilon. All right. Now what happens when k, let's say k belongs to B? Let k belongs to B, then what happens? So then you look at, suppose capital M to be, sorry, capital M is, let's look at capital M tilde, which is supremum of H on AB. All right. Sorry, not, yeah, this is on AB. So which means I can take supremum of the map P on small m to capital M. That gives you a supremum page. Now this mk star minus small mk star, this will be less or equal to this, infimum will be less or equal to supremum, right? So this will be 2m tilde, less or equal to 2m tilde. That is always true. There's no problem in that. We now use this fact. All right. So we have this for k belongs to B. So let's look at the summation m mk minus small mk xk minus 1 k belongs to the set B, right, which is less than equal to lower sum minus upper sum, which is less than delta square, and that side here. So this mk minus small mk would be what? Greater than delta, greater than equal to delta. That's what it is, right? So we have on B is greater than delta. So this is summation k belongs to B. This is delta. Delta comes from here, and this is xk minus 1. All right. So this two, consider this two, this and this. Delta would get cancelled. So what we get is summation over k belongs to B. Xk minus 1 is less than delta. So this one is, we don't get this one smaller, but what we get is the length to be smaller, right? So ultimately you have to come some way out or the other. Either the supremum minus infimum becomes smaller or the length becomes smaller. Here we are getting the length becomes smaller. Now therefore now you look at upper sum of h p h minus lower sum of h for the partition P is summation over j belongs to a mi star mj star minus small mj star xj minus 1 plus k belongs to b mk star minus m small mk star xk minus 1. All right. So here what we get is it's less than equal to epsilon times p minus a, and here what we get is from e this will be less or equal to 2k and this will be less than delta. So this is 2 m tilde. This is less or equal to 2 m tilde. So 2 m tilde, and then this is delta, right? Now one can, since we fixed epsilon, so one can choose delta to be smaller than epsilon. That is always possible from here. So that will be less or equal to epsilon times b minus a plus 2 m tilde. Hence by previous theorem, this lower sum minus upper sum, there exists a partition P such that upper sum minus lower sum becomes less than epsilon times something. So hence H is Riemann integrable. Right? Any question? So next time we'll look at connection between integration and differentiation. Yeah, any question?
So the less than delta squared part of the inequality came from the fact that f is Riemann integrable, right?
Right. F is the Riemann integrable. That part
Okay.
is important. Yeah. So this Riemann integrability of F would give you this. Yeah. Any other question? So the properties I left out here will be part of the assignment coming next. Okay, I'll just type them up and put it. But you can start writing these things. Yeah, any other question? Okay. Okay, then we'll. So one announcement. So for now, what about Friday? Do you want to leave?
So Friday is institute holiday, right?
Friday is a holiday, is it?
Yeah, Good Friday, I think.
Oh, okay. So no class is kind of missing. All right. Okay, so you have long weekends. I think Monday is also holiday, right? Yeah. Okay. So no problem. We'll meet you again on Tuesday. Okay. Bye.